Some molecules have more than one valid Lewis structure. So let's look at ozone. Ozone is O3. So put 3 oxygens in a row. We really aren't going to do anything with cyclical structures where you have rings. So no ring around the rosy for our Lewis structures. So instead of making a triangle out of those, we're just going to stick them in a line. Oxygen has how many valence electrons? 6. And I have 3 oxygens, so 3 times 6 is 18. Got 2 and 4 in there. 6, 8, 10, 12, 14, 16, 18. Ran out of electrons. So I need to do some extra sharing. I need to make a multiple bond. This oxygen doesn't have enough valence electrons or enough electrons in this structure. This one has enough. So the one that has enough is going to share its extra. So it's going to take a lone pair and share it with that oxygen. So we'll go like that. Now, does everybody have an octet? Yes. So there's a Lewis structure for ozone. These oxygens are all oxygens, but are they the same atom? No, they're different atoms of the same element. If you had friends who were identical triplets, would they take kindly to you assuming that they were just like completely interchangeable? They probably wouldn't like that, would they? It's like, yeah, I know I look exactly like my 2 sisters, but I am me, right? I am not them. We're not interchangeable. We are different people. And so these oxygen atoms are different atoms. So why does this oxygen get the double bond and that one doesn't? There's no good reason. Could we draw it the other way? Sure we could. So we could put, my pencil only works if I hold it completely vertically. That's not challenging at all, because I needed something else today. So in this messy one, we still have octets for everybody, right? So which one of these is correct? They're both correct, and neither is correct. So we've got 2 valid Lewis structures, but in nature, the actual molecule is neither one of those. It's more of an average of those 2 structures. We can measure bond lengths and compare and look at different properties of molecules, and experimental evidence says that we don't have one single and one double bond in ozone. The 2 bonds are the same. So it's sort of between a single and a double bond. You could think of it as a 1.5 bond. Well, Lewis structure doesn't have any provision for that sort of a thing. This is one of the limitations of Lewis theory. So what do? Well, we draw the 2 structures and we put a double-headed arrow in between. And these are called resonance structures, which is kind of an unfortunate name, because I don't know about you, but that makes me think of it resonating back and forth between the 2 structures. And that's not what it is. It's actually an average, a combination of the 2. So here we have a picture of 3 dogs. There's a German Shepherd, and that looks like maybe a golden retriever. And so if these 2 dogs got together and had a puppy, their puppy might look like this, right? It's got some characteristics of the German Shepherd and some of the retriever. Does this puppy some days look like a German Shepherd and other days look like a golden retriever? No, that's ridiculous, right? It's always this combination of the 2. And that's what the actual structure of ozone is. It's a combination of those two resonance structures that we drew in the Lewis model. Okay? So it's not this one and it's not that one. It's actually a combination. The best we can kind of represent is by doing a dashed line there, sort of a 1.5 bond. But we represent it as the two possibilities with a double-headed arrow, resonance structures. In the Lewis model, electrons are localized, meaning they are on this atom, they are on that atom, or they're between these two atoms in specific places. In actuality, electrons can be delocalized. They can actually be spread over several atoms, several bonds, or even the entire molecule. And doing that lowers the potential energy of the molecule. It's called resonance stabilization. And that becomes important in organic chemistry. Any questions? Okay, so let's write a Lewis structure for the nitrite ion, NO2 minus, include resonance structures. So that's a, hey, there's going to be resonance structures. Okay, so NO2. I have to figure out how to combine these, how to attach these to each other. So one of the guidelines is that more electronegative elements tend to go on the outside. So oxygen's more electronegative than nitrogen. So it might be a good idea to stick the nitrogen in the middle and connect the oxygens to it. It's also generally true that molecules like this are symmetrical. And so you put the nitrogen in the middle, the oxygens around it, it's nice and symmetrical. So there's my skeletal structure. Then I have to count electrons. So nitrogen has 5 valence electrons. I have 2 oxygens, they each have 6 valence electrons. And the -1 charge means I have an extra electron, +1. So that's 18. Now I start putting those around. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Just kind of spread them around and see what you've got. I ran out. So I'm going to take electrons from one that has an octet to share with this one that doesn't. So I'm going to borrow or take a pair of electrons from the nitrogen and put that in here as a shared pair. Do I have octets for everybody now? Yeah. Need to finish this off because this is an ion by putting brackets and the charge on it. Now, there are resonance structures here. The resonance structures generally happen when you've got a double bond or a triple bond and there's more than one equivalent place you could put it. So here I've got the double bond between the nitrogen and this oxygen. A very equivalent place to put it would be between the nitrogen and the other oxygen. And so those are the 2 resonance structures. So I can draw it with the other oxygen having the double bond. Everything else is pretty much the same. I put a double-headed arrow in between. And same number of electrons. So those are the 2 resonance structures. The actual structure is a combination of those. Any questions? On the worksheet that we're going to do, you are asked not to draw all the resonance structures, but to identify if there are resonance structures, and if so, how many there are. If you only have single bonds, there's not going to be any resonance structures. It's only going to happen when you've got double or triple bonds, and you could put them in more than one place. So sometimes it can be hard to decide how to put things together, who to give the electrons to. And so we've got this idea of formal charge that can help us figure that out. Formal charge is something that's made up. It's a fictitious charge, a little bit like the oxidation states were made up. So the formal charge is the charge that an atom would have if all the bonding electrons were shared equally between the bonded atoms. And this is a kind of a shortcut method to figuring stuff out without having to look at electronegativities. So the way the book presents it, which is correct but I think kind of confusing, is that the formal charge is equal to the number of valence electrons minus the number of bonding electrons and half the non-bonding electrons and half the bonding electrons in the Lewis structure. If that works for you, great. I think of it differently, and I'll show you how that works in a minute. Some rules: the sum of all the formal charges in a neutral molecule must be 0. In an ion, the sum of the charges has to add up to the charge on the ion. It's better to have small formal charges than big ones. 0 is even better. Sometimes you have to have formal charge, and then you want to put it on the more electronegative element. So let's look at an example. Here we have HCN. And how do we identify what the correct skeletal structure is? We've got two possibilities. We could put carbon in the middle, or we could put nitrogen in the middle. And I'm going to also draw these down here so that I can chop them up. So if we put carbon in the middle, and we get octets, we're going to end up with something like that. If we put nitrogen in the middle, we'll end up with something like that. Both of those satisfy the octet rule. How do we decide which is correct? Well, formal charges can help us. So this is how I think about formal charges. I think of these atoms came together and formed a corporation. And they all brought something to the corporation. And now, for whatever reason, we're dissolving the corporation. And we're just going to split things up equally, and the atoms will go their own way. Okay? So what I'm going to do is I'm going to cut all the bonds in half. Okay? So when hydrogen leaves, he's going to take half of that bond, which is 1 electron. The other electron from that bond goes to the carbon. Here we had a triple bond, 6 electrons. Half go to this carbon, half go to the nitrogen. Just cut things down the middle. This lone pair, though, sticks with the nitrogen. So now we're going to compare what did that atom bring to the corporation and what is it leaving with. Sometimes they come out even, sometimes they lost, sometimes they gained. And so what we're trying to do is draw a Lewis structure where everybody just kind of breaks even. It seems the most fair. So how many electrons did hydrogen bring in? 1. And how many is it taking? 1. So 1 minus 1 is 0. Hydrogen broke even. 0 formal charge. Let's look at carbon. How many valence electrons does a carbon atom have? 4. That's how many electrons carbon brought in. And how many is it leaving with? 4. So far, so good. How many valence electrons did nitrogen bring in? 5. And how many is it leaving with? 5. It's leaving with 1, 2, 3, 4, 5. So all those formal charges are 0. That's a good thing. Let's look at this other one. Again, we're going to just cut the bonds in the middle, split everything up evenly. Well, hydrogen brought 1 and it's leaving with 1 is 0. Hydrogen is always 0. So you can just ignore him. Because he always has 1 bond, always has a 0 formal charge. Nitrogen. Nitrogen brought 5 electrons in And how many is it leaving with? 4. Right? So that's a +1 formal charge. Carbon brought in 4 electrons, and how many is it leaving with? 5. So that's a -1 formal charge. Isn't that easier than the number of valence electrons minus the sum of the half and this and that? Just cut it up. So when we break up this molecule, the nitrogen has a +1 charge, the carbon has a -1 charge. When we drew it this way, they all ended up with 0. Lower formal charges, smaller numbers are better, so we would predict that this is the correct structure. Any questions? On the worksheet, you're also going to be asked to identify the formal charges. So let's do an example here. Assign formal charges to each atom in the 3 resonance forms of N2O. And we're told that N is central. So when something is weird, we'll tell you about it. Because I would not predict that nitrogen would be in the middle of this. I'd predict oxygen in the middle because then it would be symmetrical. But that's not the case for this one. So if nitrogen is in the middle, we must have nitrogen in the middle and an oxygen on one side and a nitrogen on the other side, because that's all that can happen. Then we have to identify how many electrons. Well, I have 2 nitrogens, and they are each have 5 valence electrons. And my oxygen has 6 valence electrons, and so that's 16. So now I start putting electrons around. I've got 2, 4, 6, 8, 10, 12, 14, 16. Ran out. What do? Share lone pairs. So this nitrogen in the middle has 8 valence electrons. So I'm going to take one of his lone pairs and share. Who should I share with? How about the nitrogen? Everybody good? Not quite. This nitrogen's good, this nitrogen's good, the oxygen's short. So let's take this lone pair and share with the oxygen. Everybody have an octet there? Yeah. Now it says there's 3 resonance forms. How else could we put those multiple bonds? We still have the same connection, nitrogen to oxygen. Could we do a triple bond and a single bond? Let's try it. Let's make this a triple bond. And then we've got 2, 4, 6, 8, 10, 12, 14, 16. I can make that work. I don't want to put any lone pairs on the nitrogen because it's got 4 bonds, that central one, and that's 8 valence electrons. If I put a lone pair, it'd have too many. Could I put a triple bond to the oxygen? Sure, why not? Also satisfies the octet rule, right? Formal charges can help us to identify what form contributes the most. So these are not equivalent places, are they? One's oxygen, one's nitrogen. And so this is a little bit different form of resonance than what we saw before, where it was nitrogen and a double bond to 2 oxygens. So this is a little different, but we are still looking at just the placement of multiple bonds. Everything else is the same. But some of these are better than others. So we're going to use formal charges to identify that. So I'm just going to start out by cutting the bonds in half. Cut, cut. How many valence electrons does a nitrogen have? 5. So nitrogen brought 5, and how many is this nitrogen leaving with? 6. So that's -1. Nitrogen in the middle brought 5 and is leaving with how many? 4. 5 minus 4 is +1. Oxygen brought 6 electrons. That's a 0. 6 electrons. And it's leaving with how many? 6. 6 minus 6 is 0. Do you see how I did that? Okay, I want to show you kind of a shortcut. So let's just look at the Lewis structure for a nitrogen atom. It's got 5 valence electrons, right? 1, 2, 3, 4, 5. Nitrogen is going to typically make 3 bonds. Each of these unpaired electrons is going to share with another. So it's typically going to make 3 bonds. And oxygen has 6 valence electrons. Oops. Well, that's fine. So when I draw its Lewis structure, it has 2 unpaired electrons. Oxygen tends to make 2 bonds. When oxygen makes 2 bonds, it's going to have a 0 formal charge. Here, that oxygen has 2 bonds. It has a 0 formal charge. Because those 2 electrons that are half of those bonds are these guys right here. And so it just has, it takes away what it brought in. It breaks even. We can do the same thing for something like fluorine. 7 valence electrons. How many bonds do you think fluorine typically makes? 1. It'll take this 1 electron and share it with somebody, make a single bond, and when it does that, it has a 0 formal charge. So we can kind of predict what things are going to do by understanding this. So let's cut up these other ones. Cut this, cut this. So this nitrogen has how many bonds? 3 bonds. So I'm going to predict that its formal charge is 0. It brings in 5 electrons, and how many does it leave with? 5. Look at that. This nitrogen has 4 bonds. That's not going to have a 0 formal charge. It brought in 5 electrons, and it's leaving with 4. So that's a +1 formal charge. This oxygen here has 1 bond. Is that going to be a 0 formal charge? No. It brought in 6 electrons. It's leaving with 7, and so that's a -1. If we take these formal charges and add them up, -1, +1, and 0, they add up to the overall charge on this thing, which is 0. And those add up also. Cut this one up. Does anybody in there have a 0 formal charge? No. Nitrogen doesn't have 3 bonds. Neither of them does. The oxygen doesn't have 2 bonds. So everything's going to have a formal charge. Nitrogen brings in 5, leaves with 7. That's -2. Nitrogen brings in 5, leaves with 4, +1. Oxygen brings 6, leaves with 5, +1. The formal charges still add up to 0, though. Yes?
I have a question. So, for the structure in the middle, it's 5 minus 4. Is the 4... So I was counting electrons, so it was 2, 4, 6. But you're just counting, like, the number of, I guess, pairs, kind of?
So for this 4, come on. This 4 right here? I'm counting how many electrons would it take if I cut all the bonds in half.
Oh, so you did 8 divided by, cut it in half?
So it's getting these electrons.
Okay.
And that electron's going to the other one, and this one's going to these. So it's not 8 divided by 2 because they all had 8 valence electrons in the structure. But the lone pairs are going to go with the nitrogen, with this one. And so it's going to take those lone pairs, there's 6 there, and it's going to take this one from the bond. So we're cutting all the bonds in half, splitting them up equally. And so this nitrogen gets half of that bond, and half of each of these bonds. It only leaves with 4. Okay? Any other questions? So, which is best? How about which is worst? The worst one has the largest formal charges. That's this one, right? That one's not going to be very good. And so then we're asked to choose between these two. We can't make one with all 0 formal charges. It just doesn't, it's not possible. So we want to put a negative formal charge on an element that's more electronegative and a positive on one that's less. So here we've got the -1 on a nitrogen, and here we've got the -1 on an oxygen. Who's closer to fluorine? The oxygen. So the -1 formal charge is going to be more stable on the more electronegative element. So this is our winner right here. That doesn't mean that that's the only structure, but it means that in the combination of these 3, this one has the biggest effect. So if I showed you pictures of my children, my husband is of Japanese descent, I'm of Swedish descent. If I showed you pictures of my children, you'd say that they definitely favor my husband because they all have brown hair and brown eyes and this beautiful skin that just, they think about the sun and they get tan. And I just burn like a lobster, right? They look more like him. His genes had more influence on them. But I did have some influence. And so in this example, this would be like my husband, his genes are having more influence. These guys are also there. They're contributing to the overall actual structure of this molecule, but this is contributing the most. Okay? Let's do another one. Draw a Lewis structure, including resonance structure for diazomethane. CH2N2. We're told that carbon is central, and we're asked to assign formal charges to all the atoms that have formal charge. What that means is if it's got a 0 formal charge, you can just leave it alone. You don't have to write anything down. Okay, so we're told that carbon goes in the middle. So let's put carbon there, and maybe put a nitrogen here, and a nitrogen there. And what do you want to do with the hydrogens? Stick them on the stick the hydrogens on the nitrogens. Sometimes I forget what I just said. Okay, let's try that. We need to know how many valence electrons. Carbon has 4. 2 nitrogens, each have 5. 2 hydrogens, each have 1. That's what, 16? So just from bonds, I've got 2, 4, 6, 8, 10, 12, 14, 16. Oop, ran out. What to do? share, right? This guy's got an octet. He's happy. He's stable. So he can be generous and share with his neighbor. So we'll move that lone pair over there. I'm not changing the number of electrons. I'm just moving them around. So now we've got an octet for that nitrogen. The carbon has an octet, but this nitrogen does not. So I'm going to take that lone pair from carbon and share that with the nitrogen. Is this good? Everybody's got an octet, so that's a valid resonance structure. What are the other resonance structures? Because there must be at least one other one. Well, the last one we looked at was kind of like this, where we had two double bonds, and then we realized we could also do a single bond and a triple bond. So we can do that here as well. So we could have a triple bond with that nitrogen and a single bond with the other nitrogen. And then this nitrogen would have two lone pairs. And we could do the same thing, but give the triple bond to the other nitrogen, because just like twins, they may look the same, but they are not the same person. Those are not the same atom. Whoops. So 3 resonance structures. Assign formal charges. We don't have to do the hydrogens, because hydrogens are always 0. How many bonds does nitrogen have when it has a 0 formal charge? If we look at nitrogen, in order for nitrogen to have a 0 formal charge, it's going to need 3 bonds. Do any of these nitrogens have 3 bonds? Yeah, this one does, and that one does. So those are going to have 0 formal charge. This one has not 3 bonds. This is going to have a formal charge. Well, what's it going to be? Can we do it without marking the whole place up? Nitrogen brings in 5. And how many would it leave with if we cut all these bonds in half? It would get half of this bond and half of each of those bonds. It would get 4 electrons, right? 5 minus 4 is plus 1. So that nitrogen has a plus 1 formal charge. Make sense? What about this nitrogen? This guy over here. He brought in 5 electrons, and how many is he leaving with? 6. 2, 4, one of these, 5, 6. -1. So that is a -1 formal charge. If we look down at this other one, we can see that these nitrogens are just in the opposite situation, right? Here we've got 4 bonds and no lone pairs, like this one, 4 bonds and no lone pairs. That's going to have the same formal charge. And this one's going to be -1. Okay, let's think about the carbon. Look at the Lewis structure for a carbon atom. How many bonds do you think it likes to make? 4. Because when it makes 4 bonds, it has 0 formal charge. So that's usually a good place. Do any of these carbons have 4 bonds? They all do, right? So none of the carbons have formal charges. So there we go. So it doesn't ask this, but which of these resonance structures contributes the most? Which one has the lowest formal charges? This one, right? All zeros. So this is the best one. Questions?